Welcome back. In our last video we talked about the relationship between equilibria and the Gibbs energy. In this video we're going to explore how equilibria may shift as we change the conditions of a particular process. We of course remember from general chemistry the Chatelier's principle, where we basically were able to predict, at least from a qualitative perspective, shifts in equilibria based on the stress placed on the system, noting that a system will always change in a direction to reduce the effects of any applied stress. And of course that applied stress or that direction will shift such to minimize G. Now remember, the direction of any process that's an isothermal isobaric process will shift in a direction to reduce the Gibbs energy, noting that when that Gibbs energy is reduced, the entropy of the universe is increased, as we noted in the past and for the past couple of videos. So let's look at, for example, what happens if we change the pressure on a system. Will the equilibrium constant, for example, change when we change pressure? Well, we remember, of course, from our past discussion that delta G naught is equal to negative RT ln of K. And so we know the K will change if delta G naught changes. But by definition, delta G naught does not depend on pressure, because delta G naught corresponds to the Gibbs energy change under conditions of 1 bar pressure. So because it specifically corresponds to 1 bar pressure, it makes no sense to ask what happens to delta G naught when we change the pressure. So as a result of that, if delta G naught doesn't change when we change the pressure, the equilibrium constant will not when we change the pressure. Will not change when we change the pressure. Now, that doesn't mean that an equilibrium won't shift. It just means that the equilibrium constant will not shift. So let's consider this reaction here, where we have an entirely gas phase process, where we have 1 molecule of A going to form 2 molecules of B, whatever that might be. And let's ask what happens if we increase the total pressure of the system. Well, remember again, the idea behind Le Chatelier's principle is that the process will shift in a direction to reduce the effects of the change. So if we increase the pressure, the process is going to shift in a direction to decrease the pressure. Well, the stoichiometry in this case is such that we're going from a reactant where we have 1 molecule to a product where we have 2 molecules. And let me actually just draw the extra arrow here to indicate we're talking about in equilibrium. Then we note that to reduce the pressure, we are going to shift back to the left, because by going from 2 molecules on the right to 1 molecule on the left, we have reduced the number of molecules and therefore reduced the pressure. So increasing the pressure in this case is going to cause the equilibrium to shift to the left. Again, let me remind you, this does not mean the equilibrium constant changes, because the constant itself is not changing. It's just that the equilibrium is shifting to minimize the change in pressure. Alright, so now what about the temperature dependence? How does the equilibrium constant change when we change the temperature? Well, we'll go back to the Gibbs-Helmholtz equation, which we derived in an earlier video, which shows the relationship between G naught over T and the temperature dependence of G naught over T through this partial derivative. So we note, of course, that from the Gibbs-Helmholtz relationship, we had delta H naught, negative delta H naught over T squared was equal to this partial. We can also remember that from the expression for the equilibrium constant, there's a relationship between delta G naught over T and the equilibrium constant. So if we just simply make that substitution, where what we have done is replace delta G naught over T with the R ln of K, then we have this, and just simply rearranging this partial derivative expression here, bringing R over to the right side of the equation, we have this simple relationship which shows that that the derivative of the natural log of k with respect to t is equal to delta h naught over RT squared. Notice, of course, that we also are able to eliminate the negative sign because they cancel out. We will also note that this relationship here, the derivative of 1 over t with respect to t is negative 1 over t squared. So if we take this expression and solve for dt, where we find that dt is equal to negative t squared times d 1 over t, then substitute that for dt, and doing a little bit of algebra again, we find that the t squares cancel out, and we're left with an expression down here which gives us the derivative of the natural log of k with respect to 1 over t is equal to negative delta h naught over r. You notice that we no longer have a temperature term on the right side of the equation. So this derivative of k with respect to 1 over t is just equal to delta h naught over r. Okay, so we have this expression that shows us how the natural log of k depends on 1 over t. If the temperature range is small enough, we'll find that delta h naught does not change significantly over a particular temperature range, and we can assume that to be constant. So if we assume delta h naught is constant, we certainly know that the gas constant r is a constant. So under those circumstances, this whole term on the right side of the equation is constant. And if that term is constant, then obviously the derivative is constant. Now remember that the derivative represents a slope. So if we were to plot the natural log of k versus 1 over t under these conditions, we should see a straight line. And the slope of that straight line is equal to delta h naught, negative delta h naught over r. So in this particular case, we see the slope is greater than 0. So that means that negative delta h naught over r is greater than 0, which means that delta h naught is less than 0. So you can see from this plot that we are able to plot natural log of k versus 1 over t, and from the slope we can actually calculate delta h naught for the reaction. So that's important point number 1. A plot of the natural log of k versus 1 over t will give us delta h for the reaction. Number 2, we'll note that if the slope is positive, delta h naught is less than 0, meaning that the reaction is exothermic. On the other hand, if we get a negative slope, then delta h naught is greater than 0, and the process would be endothermic. So this shows a simple temperature dependence of the equilibrium constant. We also talked about the pressure dependence of the equilibria, noting that the pressure dependence, that the equilibrium constant doesn't change, but we will note that equilibria do shift under those circumstances. So it's a quick summary of Le Chatelier's principle to deal with changes in equilibrium. This will end our video discussion of equilibria. We'll continue in class with some additional problems associated with equilibrium constant calculations. In our next set of videos, we'll move on to the kinetic theory of gases.